Hello everyone, my name is Jihyun Kim and I'm the CEO of LOCS, which is located in South Korea. I'm very happy to be here as a NILM researcher. So today I'm gonna talk about the non-intrusive log monitoring based on deep learning and over signatures. Before I start the talk, I'll let you know briefly explain what LOCS is doing. We use artificial intelligence to predict the energy demand and the equipment failures in buildings. And we build the energy analysis platform so that the existing EMS can provide the AI service to the client. And so the user can easily implement artificial intelligence models without a detailed knowledge of deep learning or machine learning. And the generated model is easily linked to the client's EMS via RESTful APIs. So the figure in the right side is the process of our business models. Based on the environment data from the buildings, our system, the power peak time is predicted. And this information is used to adjust the charging and discharging schedule of the ESS. So the clients can control the peak value of powers. Okay. If you have a question about our business, let's talk about it in the break time. Okay, back to the energy distribution. Here is the contents of my slides. Okay, this paper describes methods of applying deep learning to non-intrusive log monitoring. So, and based on the previous works, we defined 3 problems. And to address these problems, we propose a novel signature and deep learning architectures. So in the previous problems, so many models, so many energy distribution models based on FHMM and its variance. But we find some problems in the data perspective using the low sampling rate. The model could not effectively classify the multi-state appliances and the appliances having the similar power consumptions. In the model perspective, the performance is dropped rapidly as the number of appliances is increased. So the one way to solve this problem is using the high sampling rate, but it is very hard to apply to the commercial service because of the high cost and the data throughput. So here we summarize the problems. The model what we use in this paper is recurrent neural networks. It's one of the deep learning models. So it is enabled to learn the sequential data. But if you use only RNN, you cannot, the model cannot learn the long time sequential patterns because of the vanishing gradient problems. So we apply the LSTM to the hidden layers. And so the powers, the original power, sequencer power is gonna be the input of these models. And the alpha layer represent the on-off state of each appliances. And one of the most important steps in deep learning is to find the proper methods. The methods is in the slide, the pre-processing and weight initializations and regulation and optimizations. But unfortunately today I'm not gonna be explain about it because of the time limits. So please refer my papers for in details. So we select the proper method through the experiment. For example, the activation is hyperbolic tangents, and the weight initialization method is case initialization, and we use the optimizer and atom optimizers, and the regularization is dropout. And before we use, before input the power signals, we have to normalize the input data. So the pre-processing method is G-scored. So today I'm gonna focus on the novel signatures. The key idea of the signature is to separate the original signal by the reflection rate and subtract the one variant signal from the other variant signals. So to calculate the novel signature, so we have two algorithms. The first one is a variant power signal generation algorithm. It's not so difficult. The original power signal P and the reflection rate alpha is required, and the output is the variant power signals. So in the first step, the VP is going to be initialized zero, and in the second step, the for loop will be started from 1 to time sequence length, the length of time sequence t. And in the third step, just do subtraction operations for the current power P and the variant power Pi minus 1. And after calculation D, this information will be used for the update the current variant power with the reflection lanes. So let's check the effect of the reflection light. So here is a three graph. The first graph is the original power signal, and the second graph is a variant power signal when we set the reflection light 0.1, and the third one is also variant power signal when we set the reflection light 0.01. So as we can see, the smaller reflection rate, then the scale gonna be down, and the pattern is gonna be smoother than before. So after generating the variant signals, we have to calculate the novel signatures. So the two variant signals are required, and the output will be the novel signatures. So the algorithm is simpler than before. Just calculate the subtraction operation between two variant signals, and then calculate the novel signatures. So we summarize these procedures by the figures. The first graph is original power signals, and in the second graph, there is a two variant power signals in one graph. After subtraction operations, then we calculate the novel signatures, which is in the third graph. So this means the novel signature means the variation of the power consumption. So we use this information as an input feature of deep learning model. So to validate our model and the signature, so we took an experiment. We use three data sets, which are UKDL and RDD and our private data set. So here is the effect of novel signatures. We trained two models having, the first models having the original powers, and the second model having the original power P and the delta P. So, and we use, the number of appliances is 6, and the combination of it is 64. So we check the accuracy toward the 64 combination cases. In the graph, the yellow one is the first model, and the red one is the second model. And we can see that the red one, which is the second model, classified many cases than the first models. So, and and in case of the performance of each appliances, there are 6 appliances in the graph: air conditioner and washer and dehumidifier and oven and TV and toasters. And except the dehumidifier, most of the cases, the second model the performance of second model is higher than the first models. But we have a curiosity about the dehumidifier's cases, so we analyzed the data of the dehumidifiers. So for the comparisons, so we look into the pattern of the dehumidifier and washers, and so then we can find that the pattern of the washer is fluctuating, but the dehumidifier is very simple. So we thought that the novel signatures can be fixed to the similar value if the pattern is simple. So we thought that this can be the reason why the performance of the humidifier is low. So we train more and more, and after 4,000 epoch train, the humidifier's performance was higher than before. At first, the F1 score was 0.65, but now the F1 score is 0.82. So we know that the simple pattern could be learned slowly, but this problem can be solved with the more trainings. And to find out the robustness of our models, we took a test with increasing the number of appliances. We select the 15 appliances from the House 5 of UK Dale. Now, of course, and when the number of appliances 2 and 3, it is very high performance because the problem is very simple. But aside from that, whenever we add the appliances, the performance was increased or decreased. So we want to know the reason why this kind of result is happening. So we try to figure out which appliances are added. So from 13 to 14 appliances, the added appliances was the home theater amp, and in this case, the performance was increased. And from 7 to 8, the added appliances was core to server, and in this case, the performance was decreased. So you can easily check the shape of the patterns. So, and when the performance was increased, the added appliances, the pattern of the added appliances was fluctuate shape, but the other cases, the pattern was very simple. So the performance is increased when the appliances have many variations. And we wanted to find out what is the similar power consumption. What if the appliances having the similar power consumption? The model can classify the appliances when having the similar power consumptions. So we select the 11 number of appliances from the UK DAILs, and we train the models. And in the right table is the result of our performance. So you can see that the model can well classify, even though it is appliances which having the similar power consumptions. So for overall performance, we experiment for all houses in UK Dale, and the left table shows the overall performance of our models, except the house one, which having the 53 appliances. The rest of the cases, we satisfied the result. And we implemented FHMM, which is factor-related Markov models, and take a test with the same data. And here is a result on the right side. Then you can see that our model, the performance of our model is nearly twice as high. In the last experiment, we try to take a test. We try to take a test for all houses in REDD, and here is the result of our experiment. And we compare the existing FHMM and its variance. There are FHMM and additive HMM and HIFHMM and our models. Then you can see that our model is outperforming than other models. So for the conclusions, we propose two alternatives in order to solve the problems. So through the experiment, we could confirm that the signature can be efficient for classifying the multi-state appliances and the appliances having the similar power consumptions. In comparison with the existing models, our model is outperforming than the others. Thanks for the listening.